My name is Xinhu Yu. I'm the chair of RMIT Professorial Academy. I'm chairing this distinguished lecture as well. This is just the one. The academy was established in 2019, consisting of 20 RMIT distinguished professors who are the prominent researchers and academic in the university. So the role of us is certainly there's three roles. We act like a think tank, advising university on the strategies. We promote universities, and also we represent universities. So today is last year we have two distinguished lectures, and this is the first in 2018. So we are very glad to have distinguished Professor Mike Xie to give us a talk. So this is going to be very interesting. When Mike sent an email to me, say, hey, here's the talk I'm going to say. And I look at it, I say, can you make it as simple as possible? Because we have a very different, wide range of, people have different knowledge. So he made it. So I think the title is great. Make something beautiful. We know, when something is beautiful, it's expensive as well. But it's also trying to make it efficient. So I just have a very quick introduction of Mike. Mike is distinguished professor in RMIT. He's very well known around the world. If you look at his CV, he received a number of very significant awards. For example, the 2017 Clooney Rose Innovation Award from the Australia Academy of Technological Science and Engineering. He also a recipient of 2017 Michel Medal by Engineering Australia for his work in mechanical engineering, which is surprising. I was surprised he was civil engineer, right? But now he got a mechanical engineer award. So, and he has done many work, more than, I think one of the things I found Mike is actually a great example of translation from research to industry application and vice versa, which he has done very well. So I think without any delay, let's welcome Mike to deliver his lecture.
Thank you, Xin, for your introduction, and thank you all for coming all the way to this lecture. It's a great honor to present the first distinguished lecture of RMIT University. I grew up in a small town in Jiangsu, Changzhou. This is what it looks like where I grew up. This is the Grand Canal connecting all the way from Beijing to Hangzhou. But at that time, I wasn't appreciating how lucky I was to live in such a beautiful environment. My parents always asked us to study hard, to go to big cities to look for opportunities, which I did. The first city I went was Shanghai. This is a photo of Shanghai, and you will see this kind of buildings, miles and miles. And then I went to London or in Britain to study, come to Sydney. My first job was in University of Sydney. On the left-hand side, you will see, some of you may recognize this building. To me, it's the ugliest building in Sydney. This is the UTS building on Broadway. When I walked home every night, I would see this building. Then I came to Melbourne. I was living in Footscray, and when I drive to work, I would see these two buildings in Racecourse View. I think some of you know these buildings. So these are the kind of buildings we see in big cities. And after 40, 50 years, nowadays when I go home, I really appreciate how lucky I was. And on the other side, when China become rich, and we are doing something different. So because of the wealth generated and the exuberance, all this irrational exuberance, we are creating monstrous buildings like this. And in the newspaper, we were actually boasting how much steel we used to construct this world record stadium. And there's other buildings created. So on the left is the CCTV tower of China. On the right-hand side, it's the headquarters of People's Daily. And so it resembles some human organs rather than innovative buildings. So what I'm going to share with you today is how because as engineers, we always ask us questions like how we can create some beautiful structures and also it's efficient. So not only can we save the materials, we can also create something interesting and beautiful. And one of the contributions I made to this field, I'm an engineer, but I have many friends in architecture. So we come up with a very simple idea. So if you want to design a better structure, you can actually start from any silly design and look at what you have got currently and remove those unneeded parts. Those most inefficient parts you can gradually remove from your design. And then gradually you will end up with a structure. That structure is not only efficient, it looks very beautiful, just like what you see in nature. I will show you some examples soon. The advantages of our simple idea, it's so easy to understand. I'm sure when I show you examples, you will see why we are getting this kind of shapes. And also it can be implemented very easily. When people read our papers, they can spend a few hours, then they can do exactly what we do on the computers. So I show you the first example. Say, if we want to design a structure for these given conditions, there's 1 point fixed, I apply gravity. I want to know what would be the best shape to satisfy these given conditions. If we don't know the result, the answer, doesn't matter. We can just start from this square shape, and then we can do a simple analysis of the structure. We would find the stress distribution of the structure, fix here, apply gravity, and these purple areas, they have no stress. It indicates these corners, they are not useful from the structural point of view. If you remove these parts, it would not affect your structural performance. If they are not useful, why would you keep them? So you can delete all these inefficient materials step by step, and you come up with something more efficient, and it's interesting. It looks like an apple. And it can continue to evolve, and you get a small, tiny cherry. It's just a coincidence. And when I published this work, a professor in Cambridge, he said, I can do better, because I only use one material in my model. So he started to put a different material in the core, and by changing the relative stiffness, he got a series of pairs and many other things. We are not just getting some beautiful pictures. If you compare the two designs, on the left, you can see different colors throughout the whole structure. On the right-hand side, we see the same color on the surface. So we got a design which has uniform surface stress. So because this is the criteria we use. If you have low stress, we delete it. And if you use different rules to satisfy different design objectives, you will get different shapes. Because the idea is so simple, it has been utilized by many engineers and architects, material scientists for many different applications. So you can design a building by controlling the drift of a building, the top of the building, or you can change the vibration frequency for buildings under earthquake or wind. We also did a project with Boeing several years ago for maximizing the buckling load of a composite aircraft wing. And we are lucky to have another Boeing student in the audience. James is working with us on extending this work to the aircraft design. So I'm going to show you some of the examples we have done. So when you design a structure, really depends on what material you use. You will get totally different shape. So some of you may have seen the steel cable bridges. These cables, they're good for tension. The cables cannot sustain any compression. So if your material is suitable for tension, then your final structure should be predominantly in tension. I show you one example, you will understand how it goes. Because your final structure needs to be in tension, you can start again from any silly design, and then every time, every step, you remove the areas with the highest compressive stress, and you will end up with a material only in tension. So this is a very simple example. So I fixed 2 points, and I apply the gravity, and I want to find a shape which would be suitable for, say, a steel cable or some membrane structures. So every time I remove the areas with the highest compressive stress, then I will get a catenary shape. So when you hold a metal chain, that shape is a catenary, and you would only have tension throughout the whole structure. Not only have I got a shape for the structure, it also indicates where you need more materials. So on the 2 sides, because it's supporting half of the weight of the structure, you have more materials here than at the bottom. Here the forces are very small, so the relative size is also small. And when if you see around us, most of our structures are made of concrete. The concrete is good for compression. So if you want to design a structure for bricks, masonry, stones, and you want your structure to be in compression. And again, you can start from any design, and then every time you remove the areas with the highest tensile stress, and so remove all the areas in tension, you are left with a structure which will be in compression. When I was doing this work about 10 or 12 years ago, I was very lucky that I have a colleague, Professor Mike Xie. Some of us know him. He's a very well-known architect. He's a chief executive architect for this famous building in Barcelona. So at that time, Mark was working on this passion facade, and there's columns on this facade. There were very few drawings left behind by the original architect, Gaudi. Gaudi started designing this structure about 100 years ago. And at that time, he was using those physical models with chains and weights. If you look at this structure, every point on the chain is in tension. And what Gaudi did, he put this model upside down, then everywhere would be in compression. Because he was building this church using stone, which is similar to concrete. It needs to be in compression to be efficient. So if you turn this model upside down, you will get a shape which would be suitable for a masonry structure or stone structure. And if you go inside this church, you will see a lot of interesting models. This is one of the models inside, and these chains will be in tension, and there's a mirror underneath. I took a photo from the mirror, and this would be the structure Gaudi would use to build his structures. You can compare the two. You can see the architecture elements. They are very similar. And if you walk around Barcelona, you will see many of Gaudi's creations similar to this shape. Once we got our method, we can actually replicate what Gaudi did 100 years ago very quickly, because when he created these models, it needs 6 or 9 months in order to get a model working. And also, he could only consider gravity. But with our method, you can put all the forces in, and to see which areas are in tension, you remove them, you were left behind a structure which would be suitable for the stone material. So this would be what we get for the passion facade, which is very similar to what Gaudi's original drawings, and what Mark Xie finally created using parametric studies. And it also depends on what forces you use. So if we build this church in Shanghai, you would get a totally different shape, because in Barcelona, the earthquake loading is small. But in Shanghai, Tokyo, these cities, you have to have very high resistance to the lateral load. And we actually tried that. If you put down very strong the earthquake load, you would have additional bracings in order to resist forces in the horizontal direction. These are a series of studies I did with Mark Barry. So if we want to create 3 columns on a slope, and starting from this, by deleting the areas which has high tensile stress, within a few seconds, we can get a shape like this. If you go to Barcelona next time, have a close look at these columns on Passion facade. And these columns have exact shape as what we can get from our simple rule of evolutionary structure optimization. All we did is we start from any design like this. There's no bias. It only says there's 3 columns. If I remove areas in tension, you will get a shape, a beautiful shape, and just like what we were seeing at the real church in Barcelona. In a 3D version, say if we want to build 2 columns on a flat surface, so you start from this. Every time we remove the areas with the highest tensile stress, you get some strange-looking column like this. And people consider Gaudi as a genius. He actually got this design about 100 years ago using his physical models. But if we go back to the basic mechanics and apply the simple rules of removing the tensile materials, we would get exactly the same shape as Gaudi did for his famous church in Barcelona. And later on, we improved our method. Previously, we can only remove the inefficient parts from the current design. We can actually do the reverse, say, like the apple example. You can plant a seed and let the seed to grow into apple. So you can, in structure terms, you can strengthen the most critical part in your structure by adding material to where it is most needed. Or we can do both ways. So you can start from any design, then while you're removing the most inefficient material, you can add those material to where it is critical. So we call it bi-directional evolutionary structure optimization method. So it would be much faster and it's more efficient. So I show you one simple example. Say I want to design a bridge type of structure. So I have a deck with uniformly distributed force, 4 points fixed at the corners, and I leave a gap in the middle so that vehicles can go through. All the rest will be decided by the computer where to put the material. And your initial design can be also very simple. So I have a plate, 4 columns, and this can also be a bridge, but no one will pay you consulting fees for designing something like this. It can break very easily. There's a stress concentration, but it doesn't matter. We can start from this initial design and let the computer to decide where to add the material and where to delete. So you will find some of the earlier material added is removed later on. So we are not doing some local modifications of a design. That's what people do in consulting office. They have a design and then do some assessments. Oh, this part needs to be strengthened a little bit. So they do a simple change. We actually change the structure concept from this to that. It's not a simple local modification. The structure concepts of the 2 designs are completely different. We got an arch bridge with additional members like the tree branches we have repeated seeing in Gaudi's designs, so that the whole structure has very uniform stress distribution and uniform structure performance. We have done many other examples. Say this one is to design a atrium in a hotel. So you have 4 columns. You have very few columns. You want to transfer the loads from a few columns to upper levels. And our process would enable you to find the best load transfer system. Again, it looks like what we see in nature, those tree branches. We can also do the dynamic optimization. So if we have vibration frequency through our process, we can find a design with the highest frequency, or you can increase the first 3 or 5 frequencies of the structure. We can have multiple constraints. So you can, for this building, we can minimize the deflection at the top of the building and also control the frequency. So by redistributing these uniform shear walls, we get a bracing, and the structure performance will be increased significantly, not for both static and dynamic criteria. We have also tried to apply our technique to periodical structures. So I show you one simple example you will understand. So this is a bridge, say, a few 100 meters long, but it's made of identical units. So if we apply our rule by first, say, divide the structure into a certain number of units, and when you change one unit, you change the corresponding locations at all units. You will get a periodical optimum design. This example would be easier to understand. Say, this wheel has 8 identical modules. When we apply our method, say if we want to delete any material here, all the corresponding location would have the material removed. And you apply all the loads you were experiencing when you are driving the car. In our case, when you are accelerating or turning or braking, all the forces on the wheel would be different. You need to consider all the major load cases in order to decide which part needs to be removed or remain. Depending on how many cells you want for a wheel, you can get totally different designs. This was done by one of my PhD students. He got these pretty pictures, and then I asked him whether these are correct or not. He walked around Melbourne Street and took 2 photos, and he found this. So this is what he got using our simple bi-directional evolution structure optimization. These are Cadillac, BMW, 17. They're almost identical. So again, this is not a coincidence. This is because our design objectives and BMW and Cadillac's, their objectives are the same. We want to design the lightest possible wheels which has certain structural performance. So they have spent maybe 40 or 50 years to improve their designs, but using our technique, we can develop the next generation of motor vehicles very quickly. Around the world these days, the electric vehicles is very popular, but the loading on the wheels are quite different. Because of the heavy batteries, the loading on these wheels would be completely different from what you see on BMW or Cadillac. But when we design a new wheel, we can apply these new conditions and get up very close to the optimum design very quickly. And I started doing this work when I was in the aeronautical department in the University of Sydney. And because weight reduction is of critical importance for aircraft, that's why we have been working with Boeing and also COMAC in China, try to apply this technology to aircraft. We had several collaborative projects with these companies. But strangely, unexpected, the people who became very excited about our technique, was a group of architects. And so about 15 years ago, famous architects around the world started using our technique. I think it's mainly because of the organic shape we were able to create. It looks so beautiful. It looks like what you see in nature. So they started to make buildings. So this was the first building designed using extended evolutionary structure optimization, which was based on my work. This was built in 2004 in near Nagoya. There are many other buildings. I give you a few. This one, some of you may have heard that the Pritzker Architecture Prize, this is the highest prize in architecture. It was awarded last week to a guy called Arata Asazuki. He actually was one of the first architects using our technique to design buildings. This one was in Qatar. It's actually very similar to the bridge example I showed you. If you're using our software, you fix these 2 points, put uniformly distributed load on the top. Within a cup of tea, you will see this beautiful image on your screen. It's as simple as that. It's not just a beautiful picture. It has been built. This was a photo taken in 2012. I once passed Qatar airport, so I took a taxi and went to take this photo. So I took this one. So it has been built. And in China, Shanghai, there's another famous building, Himalaya Center, these strange shapes. Next time when you see it, it's not strange anymore. It's based on our simple rule of deleting inefficient material and to get a different design. So these are all based on the extended evolutionary structure optimization method I originally developed. I have some other architecture friends who have been using my technique to build these different structures. This one has been done in Shanghai as well. I also tried to, she mentioned that I was good at translating research into real project, but I tried and I failed terribly in Australia. I give you one failed example of this. It's a lesson I learned to move to the next step. So about 10 years ago or 12 years ago, the Vic Roads was doing a revamp of the Monash Freeway. There are several footbridges which they were calling for proposals. And I was very excited because we thought we could use our technique to design a better footbridge for Melbourne. I think we did a very good job. So we were given the information how wide the Monash Freeway was, 45 meters, and the boundary conditions, depending on where you build the bridge. So if you're building against two solid rock, you would have this. If you're supporting here with a simple support, a roller, it would be a different structure. So we did a series of studies. This is what we proposed to Vic Roads. This is near Malvern Station. So next time you could have this bridge there in 2007. We presented it to Vic Roads because this is really too dramatic. People haven't seen this kind of thing. This is before Asazaki built his structures in Qatar and Shanghai. So Vic Roads said, look, it's impossible to build a bridge like this. It's actually, the deck is here. So if you walk through this bridge, it will be a really interesting visual experience. So they said, no way, this can't be built. So in their great wisdom, they built this. This is the Malvern Station footbridge, which so they chose the safer way to construct this. I was very disappointed because they said it's not possible to build. I built one in the lab. It's building 10 in the old civil lab. The circle has 6 identical pieces. So I made a reusable mold. This is timber mold. This foam will become the hose. So I put the steel reinforcement weld the connections, put in the concrete. 6 identical pieces, I put on the bolts. I can construct this very easily, 1:4 scale section of that bridge. So I wasn't successful to convince Vic Road. But in retrospect, I can understand, because this is something too ahead of the market. The market wasn't ready 10 years ago. But if I do this again now, I think I have a much better chance to convince people in the authority to take a risk and do something different in Melbourne. I tried my hands in China as well. So this is a proposal in Suzhou. Again, this beautiful design is from a very simple rule of removing inefficient materials, so redundant material from the structure. The byproduct of that simple process is this beautiful design. So this is a proposal. We are still trying to get it built in China. And not that we actually did a series of work. Last year, I worked with a famous architecture firm in Shanghai called Atelier Archimixing. So we proposed a series of footbridges in Huangpu River. It's a famous river in Shanghai. We can also apply our technique to small-scale structures. This is a hot area of metamaterials. So by applying our technique, we can improve the material properties of these repeated periodical microstructures. In this case, we have been trying to maximize the back modules. So under any pressure, this structure would have the least amount of volume change. The next one is a microstructure which can resist the shear stress. If you put on shear stress on this material, because the material has been arranged on the diagonal direction, it can have very high shear resistance. Or we can design a microstructure with specified stiffness in different directions, like a bone. When you want to create a replacement for a piece of bone, you want that material to be having similar material property like the bone being replaced. And normally you would have different stiffness in different directions. We can get exactly the same stiffness ratios by designing the microstructure. So this is a functional gradient. You can have changes along the length and have a gradual change in the material property. And this is one of the material we have designed. So normal material, when you have compression, it will expand laterally. So in our case, when you compress it, it actually shrinks laterally. So it does the opposite. So this is the negative Poisson's ratios material. And there have been a lot of papers written, but we were very early to be able to produce something which we can show to the people how it behaves. Another one, this is a metal version of the negative Poisson ratio material. So the shapes are a little bit different from the rubber one. You can see rugby ball shapes. So a horizontal one, a vertical one. This is a 3D. It's not just 2D. It's a cube. So when you compress it, it will move in laterally. This kind of material has a lot of application in defense industry. We have some contract with DSG, used to be called DSTO, trying to incorporate this kind of material to resist the shrapnel penetration to armored vehicles. We have developed another material which behaves different from normal situation. So normal material, when you put it on compression, it will shrink. So in this case, I put my material in a freezer bag and put a tube to suck the air out, which is the same as putting uniform pressure on the material. If I do that, if I suck the air out, put the pressure, it actually expands under pressure. This is purely because we have designed our microstructure so it will have maximum deflection or deformation in a certain direction. So I can change the shape of those cavities to make it grow in 2 directions. We have designed these kind of materials as well. So you can make it grow in 1 or 2 directions. It's not possible to grow in 3 directions under uniform pressure. We can also make different holes so that under any pressure, the length of the material would not change, or the cross-section area would not change. So by simply changing the shape of the cavity through our optimization algorithm. So this material has applications in biomedical field. We had 2 contracts with wound management CRC. It's because our special material like this. So, I'm going to talk about something. So this is the connections in civil structures. They are very complicated, and normally you need to say these are cast, these are weld. And one of the projects we have been working with Arab is try to use 3D printing technology to realize these complex connections. So traditionally, we would design the columns and beams, and in our project, we would like to use standard, say, steel columns, steel beams, but we design every connection, because you can find these forces in every member easily, and then using these forces as input, you can design the connection. So your initial design could be a solid ball, and then let the computer decide which area need to be removed to make it lighter. So this is one of the examples. So I fix here, put a bending moment here, another bending moment there, then I can get rid of all the unnecessary material to produce the most efficient connection for this given loading condition. We have done many different nodes. In this case, I fix one point, put a shear force here, put a shear force. You get, after you remove inefficient material, you got this beautiful connection. So if you come to a future building we are going to construct, when you come to a room, the connections are not like these boring squares. Every connection is a piece of artwork, just like this. And these are some of the 3D printed metal nodes. I have some at the back. When we finish, we can have a look. So at RMIT, we are very proud of the facility we have at the AMP, Advanced Manufacturing Printing. We can print many of our nodes. So this was done at AMP. This was done somewhere else. But there's one critical thing about the metal printing. Although you can say, oh, it can be done, but there's 2. When I brought this node back to my friends who are doing the real project in the field, they asked me 2 questions. A, how much does it cost? B, can you certify your node? The first question, when I did some calculation, I give him the price. It's about 1,000 or more times what of the normal price they would use in the construction industry. The second one is the possible defect in these metal printed parts. So eventually, I actually stopped doing the direct metal printing, started to do the casting, because you can print the same model using wax very cheaply, and you can print very large wax models. So Huazhong University of Science Technology, they can print those wax models 1.2 meters big. Or if it's 3 meters, you can print 2 pieces and stick 2 wax models together. Then with the wax model, you can create a shell outside the wax model, and that shell can be used to cast metal. So the next one is the shell. So this is a ceramic shell you can get after you dipping your wax model into the ceramic slurry and let it dry. You do that several times, you get this very solid shell. And you can pour the molten steel into this. So this is a very good image. It was taken in Melbourne 3 years ago. It looks like a medieval 300 years old picture. The process of casting has been there for hundreds of years. People are still doing this. But this is a perfect combination of traditional casting technology with modern techniques here. So here, we actually used the latest topology optimization technique to create the shape. We use the 3D printing to print the wax. And so the advanced manufacturing technology is here. But the last step is casting. And this, we have several examples on display at the back. So when you see this node, this one was cast. It answered that 2 questions I was asked. One, the price. This would cost a small fraction of the direct metal printing node. The other thing is, because the last step is done through traditional casting technology, it can be used tomorrow because there's standards. People have been using casting for real projects for many, many years. So I have 10 more minutes. I will go quickly about some of other things we have been doing. So the topology optimization technique can be used for many things. We actually made some jewelries, but I deleted that picture. I show you some of the furnitures we have made. This is a stool we made. So by applying the load, then we can get this structure, we can 3D print. If you come to my office, you can see some of the tables my student made for me. So this is Charming, one of the students there. He made this table for me using our technique, using our software to remove the inefficient materials. I want to show you the slight difference. Initially, I want to make a table using 3D printing. So we generate this shape. I send it to print. The bill come back. This leg cost me 700 Australian dollars. So if I want to have a table with 4 legs, it's almost $3,000. It's too much. I didn't get the budget. Shin didn't give me any additional support for that. So I changed the strategy. So instead of doing the full 3D printing, this is a 2D laser cutting. So it's made of 4 plates. So it's a 2D plate. You do laser cutting, and it can be flat packed. It takes very small volume. And this cost, the whole thing costs about $100. That one would be $3,000. And we bought a tabletop, the glass, $99. So this is $200 table. And it looks very nice. Sorry? This is from, the tabletop is from IKEA, but that advanced technology is underneath the glass. We want the glass so that we can see what's there. Yeah. Yeah. And the other issue is these 4 plates, we need to have the glue to glue them together, which is actually very tedious because you need to have 2 people hold it and wait for a long time. So we improved it. So this one has 3 plates. We use a dovetail system. So the 3 plates, you can just slot into each other. Then you can assemble them. So you can put it in a suitcase because it's so small volume. And when you get there, you can assemble it. we also tried our method to June. So this is the initial design. And you apply the load. Because when you fly, you are turning, and the forces on the 4 propellers are quite different. So if you're taking off, so some of the loads in one propeller would be much higher than the rest. So I think we consider maybe around 15 load cases and removed the inefficient parts. We can get a very lightweight and organic drone, just like this. It flew perfectly. We tried this in our campus. It can, it's also at the back. We didn't bring the battery, otherwise we could fly in the room here to show you. I actually tried very hard to put some of my technology into real structures. I'm making some progress. So this is one of the projects we have designed. So in this one, we designed 48 tree-type columns, just like what Gaudi did in Barcelona. We are having these 200-meter buildings to be completed in the next few months with 48 trees, just like this. And the one in white, it's me. I was so proud to inspect my team's work when this mock-up, this one-to-one model was built about 18 months ago. This is one of the job, our current job. So this is an observation tower overlooking a famous lake in China. And this was designed by an architect. And the owner wasn't quite satisfied. He said, oh, we want to create a landmark building for this structure. Can you find someone who can do better? So people refer to us. They know we like doing some crazy things. So we started redesign this observation tower. So this is about 150 meters or 200 meters. About 200 meters. So there's 2 lifts going up. There's a artificial wetland here. And so first we need to set up all the loads. So you have the gravity on the tower, you have the forces on each floor, and the lifts, and the artificial wetland, winds from 4 directions. Once we put all the forces in, we can start to evolve to generate different designs. So again, by deleting those inefficient materials, we can come up with a totally different design. So this is one of the proposals. We can actually control the member sizes to make it thicker. So this is one design. In another one, it's a similar process, but with thicker members. So these are some of our proposals. So I just go quickly. We are hoping to get this built in the next few years. And there's one thing we realized through our work is we need to have much closer collaborative relationship with the architect. Because traditionally, in China, in Australia, in many countries, the architect would produce a design, and then they give it to the structural engineer to say, look, you design the thing to make sure it doesn't fall. But the structural engineer wouldn't be able to make much changes to the shapes or forms of the design. But if you are able, I'm mainly a structural engineer, but if you are able to get involved in the project very early, so before they decided the design, you need to start to talk with the architect in order to co-design that project. Then that would make a big difference. In this case, we actually have been talking to the architects very constantly. Like when we produced this design, the architect said, no, because this is an observation tower, I can't have a solid wall here. You need to have transparency, or you need to be able to see through. We can achieve that by simply putting a thicker walls at the bottom. if you use thicker plates, you can get additional holes in these faces. So it's only a matter of a proper dialogue. It's rather than just one-way flow. It's a two-way dialogue in order to come up with a design satisfying both the architecture intention and the structural performance. One of the, our current research is when we deal with the mathematicians and when we do optimization, they always say, is your solution the absolute best or the unique solution? That's what the mathematicians want to ask. But these days, actually, I want to do exactly the opposite. I don't want a single solution. I want many solutions. That's because I've been working with architects. They hate to give a solution that I've got the best solution. If that's the case, what's their job? They want choice. They want input. So what we want to do is to create many solutions. All these solutions that look dramatically different, but in terms of structure performance, they're very close. So this is something, and we have made some good progress. So this Qatar Convention Center, if we only consider the structure performance, we would get something like this. But because this is the existing design, we can't build this in Melbourne or Shanghai. It has been there. People have been won awards. But the situation is quite common. You have two supports, uniformly distributed load. For given boundary and loading conditions, we want to create a different looking design. This is what we have achieved. Because this is the existing solution, any material which has already appeared in the previous designs, I would penalize it. So by doing that, I get a quite different result. So there's additional trust, and the structural performance of this is actually very close to that. That's another example. Say I have uniformly distributed load on this deck, and if I only consider structural performance, you get two arches. If I penalize the material which has already appeared in this design, I get the second design, where the two arches are coming together. If I penalize both existing design, I get another one. The third one, the two arches become one. And the three looks quite different. But in terms of structural performance, they are within 3% if you consider their stiffness. So although they look different, they're from structural engineering point of view, they're very similar. So that's why we call it diverse and competitive designs. And I'll go very quickly. We have developed some software called Amoeba. It's been running on the cloud. It can create all these structures very quickly. So this is how we can design the stool. And this is a 2D version of a chair. And these are some of other things. So I'm very lucky to have so many talented students, and probably 15 of them are here. So they have contributed to the work, and we are making some new progress in our team. So thank you very much.
All different kind of discipline areas and create some of the fascinating structures. So now we just open for some questions. Any questions and comments? Yeah, there.
Does your method always converge to a solution that's stationary, or do you just have to decide on an arbitrary stopping point?
We actually have to get them to converge. So we look at the objective function. If the objective function do not change much for 10 steps, we stop. So we have a criteria to decide when to stop. It's always we have a very flat line to make sure it converges.
Thank you.
Thank you. Any more questions? Yes. Where's can we have the, sorry, can we have a speak? Yeah.
Okay, thank you. In design a category structure, if we give a minimal size constraint and give specified volume fraction, can we get a solution which matches theoretical solution very well?
When we do to prove our algorithm is working, we have actually compared a lot of benchmark examples to show that our simple rules can produce those analytical designs. We have done that in both static and dynamic examples.
All right. Any? Okay, Elena. Can we pass on that speaker?
Thank you for that great talk. I'm just wondering how much this is, well, your design is dependent on the actual materials that are used, and if you can use a combination of different materials and how many materials you can incorporate into one design, if it's a constraint or?
It heavily depends on the material you use, like what I showed, whether it should be suitable for tension or compression. You can have multiple materials. Because our technique is a simple post-processing algorithm. It's actually whatever you can analyze using fine element software, we can post-process the output and make changes. So your problem could be nonlinear material, could be large deformation. As long as you have considered this in your analysis, you can do modifications to get a new design and put it back for the analysis to assess its performance.
But if I can add to this, the practicality of things like the boundaries between materials, they would be susceptible to deformation or stress. How this is accounted for?
Yeah, we haven't considered these details yet. I keep it in mind.
Thank you.
Okay, thank you very much. Yes, there's another questions from there.
Well, thanks, Mike. Just a quick question. When you analyze the structure and then you change the shape, do you start from initial condition, or do you, how does it work? Or do you just keep going the analysis, especially if it's nonlinear? Do you start from scratch when you change the shape?
We actually continue. Yeah, if it's nonlinear, it's far more complicated. You really need to go back again to do it. We haven't done many nonlinear examples, but we did some nonlinear materials. Yeah. Both are possible, but the result will be different because it's path dependent, isn't it? Yeah. We can do both ways, and to see what difference we get.
Okay. Oh, well, there's another one. Questions?
Thank you. It's a very interesting presentation. My question is regarding construction prefabrication, because that's getting more and more popular in the construction industry. Have you considered to inform the lean manufacturing stage for that, with your design and the optimal solution for the structure, whether that can be considered also to inform the lean manufacturing stage?
One of the things we can contribute is the aspect I mentioned about the periodical structures, because the prefabrication, you have many identical components, and we can make this identical component if we can save a small amount for that component, because it's produced in such a large number, we can achieve a lot of savings. So we have been thinking about along these lines.
Maybe bathroom poles, those kind of things.
Could be, yes.
Okay, thank you. Yes, there's another question.
I have a non-engineering question. So because obviously, so you've got the architect that is using the software to produce a very unique looking design, but the design uniqueness is actually sort of inherent to the actual software. So the software in itself is sort of geared towards this very specific design aesthetic. Does it mean that as a design professional, there is a possibility of coming across IP problems by using the software from multiple design firms? Because you will inevitably get, although you say they look different, they may not look sufficiently different from plagiarism point of view.
I guess it's self-regulating. If those famous architects, if they are aware there's some similar form being built, they wouldn't produce something similar. That's why the diverse solution becomes so important. We can actually have some random process. Every time you write, because we have put some random modifications to the, say, material properties, every time you get a totally different random design, but we make sure that the structure performance is not sacrificed. Although you get random shapes, but every design has very high structure performance.
But I'm thinking more from the actual aesthetic point of view.
Yeah.
Is there a way to modify, so let's say as an architect, you can have a very sort of specific, we call it design thumbprint. So design thumbprint.
Yeah.
So it's literally like a thumbprint that sort of recognizes you as a designer, because the Japanese designer seems to be using that very natural shape, and it's become sort of his signature look.
Yeah.
So is there a way to modify the algorithm so you can have your own, the algorithm takes your signature look into, or that it will develop, some sort of a signature look?
You can actually specify some regions. We did some examples. You can say in your design, you can actually put RMIT in the design, and that RMIT is always remaining there. And you can say this area has to be a hole, or that area has to be solid. And all these things the designers or architect can control on the screen. So it's not just a black box. We want to avoid a black box too. We want to empower the architects to use our tools. Yeah.
I think we might just, given the time, we might just stop here. So you can still talk to Mike after. We have some refreshment afterwards. So please join me to thank Mike for the fascinating talk. Wow. All right.